Hello, we are the Bridge Guys, and this is our final project for foundation design. So, these are introduction slides. I'm Jeremiah Bartlett. I'm the group leader. I'm a UConn senior. We're all in the civil engineering major, and we're excited to show you our project. So, why even do this project besides the grade? Well, foundations are an integral part to all construction and is the first step before you even decide to build what building you're going to build. So we decided to evaluate two subsurface profiles, one primarily made of sand and one primarily made of clay, so we can see the difference between a optimal soil profile and a suboptimal soil profile. And for our two loading conditions, we had a normal one and an extreme load, which kind of represents, the building at capacity in the worst case. For example, when they're constructing it, when they'd have large machinery on it, in a heavy traffic day when it's car to car. And we had two groundwater conditions, a normal groundwater condition, and then a flooded groundwater condition for each of the profiles, A and B. And we wanted to compare shallow versus deep foundation, since that's been the goal of this class, is to see where shallow is effective and where deep is the most effective and when you need to use one or the other.
All right, we chose a bridge going over Route 6. It's down by UConn next to the Eastbrook Mall. It's bridge 02599. It's a two-span bridge. Each lane we assume to have about 11 feet per lane with an approximate length of about 44 feet of the entire bridge. We counted 8 eye girders underneath, and we had an approximate span length of 137.5 feet. For this bridge, we had two loading conditions, one with a normal load case and one with an extreme load case. For the extreme load case, we had a load combo of 1.25 times the dead load plus 1.75 times the live load. The normal load case, we had a pure reaction of 3,850 kips, and for the extreme load case, we had a pure reaction of 5,088 kips. So on the left side, we got our assumptions. On the right side, we have our realizations. Underneath that, we calculated the weight of the concrete deck. We assumed a thickness of 8 inches, a unit weight of 100 pounds per feet cubed. And from that, we were able to get a distributed weight of our concrete deck for 100 pounds per feet squared. Multiplying by the width, we got 4.4 kips per feet for the weight of our concrete deck.
Awesome.
So on the left side, we calculated our asphalt overlay. This is the weight of our asphalt. We assumed a thickness of 3 inches, a unit weight of 140 pounds per feet cubed. And then we got a total asphalt overlay weight of 1.5 kips per feet. For our barriers, we assumed 1 kip per feet per side. We have 2 barriers on each side, so 2 kips per feet. Our steel girders, we assumed each girder was 2 kips per feet. Multiplying by 8 girders, we got a total of 16 kips per feet. Our total dead load, we added all these numbers up together, and we got 23.94 kips per feet. To estimate our live load, we assumed 1 kip per feet per lane. Multiplying by 4 lanes, we got 4 kips per feet. Our total operational load, also known as our service load, we added in the distributed dead load and the distributed live load to get a total of 28 kips per feet, in about an approximation. Our pre-reaction, we multiplied this number by our span, our length of our span, to get 3,850 kips. For our extreme loading case, we applied our load combination of 1.25 times the distributed dead load plus 1.75 times the distributed live load to get a total extreme loading case of 37 kips per feet. Multiplying by our span, we got 5,088 kips. For our initial footings, we made an assumption of the depth of our footing as 10 feet. In profile A, the base lies at the top of the dense sand. In profile B, the base lies at the top of the medium clay. For our footing dimensions, we have a width of 20 feet and a length of 25 feet. Multiplying these two numbers together, we get 500 feet squared. Below that is our applied loadings, and then we divided our applied loadings by our area of our footings to get our pressure loads.
These are our boring log locations. We weren't able to actually get any boring logs that were directly near the bridge, so we had to go a bit of a distance. So we had to use the CTDOT's just a report on boring logs of wells. Those well reports didn't actually have like actual boring logs, so we had to idealize them. All they had were the water tables. So for our subsurface profile A, we idealized it to be mostly made out of sand, the first 10 feet having loose to medium sand, the next 20 feet having dense sand, and after that reaching bedrock. And for our normal water table, we found it to be 10 feet below the surface level, and for our flooded water table, we just have it at the surface level. For subsurface profile B, we decided to make it all mostly out of clay. The first 10 feet are soft clay, the next 5 are medium clay, and then the rest up until bedrock is stiff clay/till. And we found for this location that our water table was at 15 feet below the water or the surface, and our flooded water table was at the surface. For each subsurface profile, we did 2 tests for 2 different loadings, one for normal load and one for extreme load. At the normal load, we did with a normal water table, and at the extreme load, we did with flooded water table. Of course, we repeated the same thing we did for subsurface profile A for subsurface profile B. Again, normal load and extreme load with a normal water table and a flooded water table.
So now we're on to the meat and potatoes of the project. Let's go through the calculations. So for the shallow foundations in profile A, which is the optimal sand profile, we chose a foundation with a width of 20 feet, length of 25 feet, and the depth of the foundation was 10 feet. Now, mind you, the groundwater was at 10 feet, so the foundation is resting exactly on the groundwater line. So we use we calculate Q with gamma times dF, and we get 1.2 kips per feet squared. And I should also mention that we assume that the unit weight of the soil was 120 pounds per feet cubed. And since we were working with sand, our cohesion is 0. So we decided to choose a phi prime of 36 degrees. That seemed typical of a sandy soil. And we use table 5.3 to get our NC and Q and N gamma values. Then we use the shape factor equations to get our shape factors. Then we calculate the depth factors. And once we have all our factors, we plug that into the general bearing capacity equation. Now note here that because we're working with sand, the cohesion is 0, so those cohesion factors all cancel out. And we're not on an incline, so the incline factors will equal 1. And then we get a ultimate bearing capacity of 126.11 kips per feet squared. We divide that by 3 to get our factor of safety, and our allowable load is greater than the service load, and our ultimate load is greater than the extreme load, so that means we're in the clear for that. And then moving on, we're now going to work with the flooded condition. We have the same NC and Q and N gamma values. Our shape factors will remain the same, and our depth factors will also remain the same. We go ahead and plug in our values into the ultimate bearing capacity equation, and then we get a QU of 73.4 kips per feet squared. Divide that by 3 to get 24.47 kips per feet squared, which again gives us an allowable load, which is higher than the service load applied to the bridge, and a ultimate load, which is higher than the extreme load applied to the bridge. So we're in the clear for the shallow foundation on the sand profile. So moving on to the clay profile, we had layer 1 at 0 to 15 feet of depth, and the unit weight of that was 110 pounds per feet cubed, and a CU value of 500 pounds per feet squared. And the second layer goes from 15 to 25 feet down, and the unit weight for that is 120 pounds per feet cubed, and our CU value for that was 1,000 pounds per feet squared. So we plug that into the bearing capacity equation, which is much more simplified with the clay profile, and we use the table to the right to get our K value. And then we plug all those values into the ultimate bearing capacity equation, and here we see that our allowable capacity was 2.98 kips per feet squared, and our ultimate was 8.94 kips per feet squared. So both of these values are less than their respective loads applied to the bridge, so here the clay profile isn't going to work for us. Now, trying it again with the flooded water table, not much is going to change here, and we already assumed that the clay was fully saturated. So when we plug our values into the bearing capacity equation, we get a ultimate bearing capacity of 8.84 kips per feet squared, divided by 3 for the factor of safety, and then we get an allowable bearing capacity of 2.95 kips per feet squared. The values are very similar, and here again, the bearing capacity of the soil is just not sufficient here, so we're going to need to use a deep foundation. So to do that, we want to design our steel piles first. So we decided to use 8-section piles for both profiles, and we used specifically the HP 14 by 117, and our cross-sectional area for that was 34.5 inch squared from Engineering Database, and we got an FS value of the FS ranges, so we decided to use the lower bound to be conservative here, and we plugged that in with the cross-sectional area to get the allowable load on each pile of 569.29 kips. And for the length of the piles, we chose for profile A 28 feet and for profile B 35 feet. Now, we could have gone to the bedrock, but that would have just made the problem way too easy. You know, we want to really examine the soil properties here, so we decided to make sure our steel piles didn't hit that bedrock so we can really examine the soil, investigate, and compare. So going on to soil profile A, We split it into layers, and again, we have the 120 pounds per feet cube for the moist sand layer, and then the 125 pounds per feet cube for the saturated dense sand. And we're at the normal water table condition this time, so we're using a 10 feet depth. And we calculated gamma prime at 62.6 pounds per feet cubed. And then we calculated the stress, that would be the effective stress, from 0 to 10 feet, which was 1,200 pounds per feet squared, and the effective stress from 0 to 25 feet, which was 1,126.8 pounds per feet squared. So then we calculate Q, and we get 2.3 kips per feet squared. So then we use our phi value that we assumed before. We get the same NC, NQ, and N gamma, of course. And then we use the QP equation to get the allowable load on the point load applied to each pile. And then we use the dimensions of the pile. We have D equals 14 inches. For the perimeter, we just assumed that we decided to simplify that measurement by just taking a box around the cross-sectional area to get 56 inches. For the length, we did 15 times D, which is 17.55 feet. And then we used F equals K times the stress times tan gamma. And we use that equation for both segments of the of our measurements. So then we're going to use those equations. So to use them, we need to get our values. So we get the effective stress in each segment. Then we use gamma and gamma 2. And here we just use 70% of phi as a simplification. And for K1 and K2, we use the graph on the previous slide. And then we plug all those values into our F for each segment. And then we use those values times P and the delta L to get the sand friction. And we calculate it for each layer, and we sum the point load and the sand friction to get a total ultimate load of 217.2 kips, and divided by the factor of safety, which is 3, we get 72.4 kips. And here our allowable strength of the steel is higher than the allowable strength of the soil, so our soil is going to govern here, which is what we wanted to see. We wanted to see, we want to see the true properties of the soil. And so here we get a Q allowable that governs of 72.4 kips. So to get the number of piles, it's pretty simple. We just take the extreme load that we assumed before, 5,100 kips, and divide it by the allowable stress on each allowable point load on each kip per pile. So we get 71 piles here, and then we go ahead and do it again with the flooded water table. We calculate our effective stress in each single layer, and then we use the same K values as before to get our F1, F2, and F3 for each segment. We get our sand frictions, plug those values in to get the sand frictions at each segment, sum that all up, add it with the point load, and then we get a Q ultimate of 156 kips. And here it's obviously smaller since we have the saturated sand layers, and we get a allowable capacity per pile of 52 kips per pile. We take the 5,100 kips divided by our capacity per pile, and here we get 98 piles required to serve. So for the clay layer, things don't change up much. As before, we have the CU value of the first layer as 500 pounds per feet squared. The second layer was 1,000 pounds per feet squared. And for the third layer, we have 1,500 pounds per feet squared. We have our L1, L2, and L3 values. We thought those would be accurate enough to get a good measurement here for the QS. And then we use F equals alpha times CU, and we have 3 different alpha values to calculate our 3 F values for each segment. We calculate our sand frictions, use the point load from before, and then we get 13.5 kips per feet squared, multiplied by the area, and then we get 3.2 kips. Okay, and then for our ultimate load on the piles, we're going to do QS plus QP divided by 3 to get for 118.4 kips. Divide that by 3 to get our allowable load on the soil, 118.4 divided by 3, which gives you 39.5 kips per pile. And then the number of piles we're going to need, we take the extreme load again, divided by the capacity per pile, and here we get 130 piles required to sustain the load. Now for settlement, we calculate the elastic settlement. We assumed a mu-s value of 0.2. Of course, we have the same base for our foundation, and taking the area of the foundation and dividing that by the load, we get 7.7 kips per feet squared applied. We have an M prime value of 1.25, an M prime of 1, and then we use those 2 values to get our F1 and F2, and then to get our IF value, and then we plug all that in, and we get an elastic settlement for the sand profile of 1.67 inches, which is quite significant. It's obviously not going to be appropriate here. And for profile B, similar process, but we take the A2 and A1 values that we got from the graph, and then we have the same Q naught. Our ES, our modulus is the same, And here we get a settlement of 3.2 inches, which is very significant and would not be sufficient for this design. So comparing the results, we have we needed 98 piles in the flooded condition for profile A and 71 piles in the normal condition. For profile B, we needed 130 piles, which stayed the same through the normal and the flooded condition, just because the clay conditions didn't change much when we had that flooded condition. The clay was pretty weak from the start. You're still going to need that 130 piles no matter what. So closing out with our recommendations and observations, the shallow footing was feasible only in profile A under the normal water table. It failed under the flooded water table conditions, and the design is completely unsuitable in profile B due to settlement. So the deep foundation is of course recommended here to veer on the side of safety. The drilled shafts would be sufficient. It's just that in this case we didn't drill down to bedrock, so we can really examine the soil profiles to see how a sand versus clay decides what you're going to need in terms of support. And drilling down is much more efficient. You're not going to need nearly as much steel, and it's much more economical. And to fit 130 piles into a 20 by 25 foot area is just really infeasible and extremely costly. So the moral of the story is that a deep foundation embedded into the bedrock is the best way to go here. Thank you.